Hello and welcome to another Decision Maths video. This time we're tackling question 4 of the October 2021 Decision Maths paper by Edexcel. And we've got a network. And we're told that we've got direct roads between 6 cities represented in this network. And we're asked to perform Floyd's algorithm to find the complete network of shortest times between the 6 cities. An initial route matrix is provided, but we're asked to set up the initial time matrix. So, the initial time matrix from a vertex to itself will always be a dash. So we're going to add that in. And now we're going to spot this graph is undirected. It's not a directed graph, which means that it's also going to be symmetrical. So the entry for A to B is going to be the entry for B to A. So, we only have to fill in half this diagram. A to B is 57. A to C is 95. A to D is 150. A to E is 63. And A to F is 230. B to C is 72. B to D doesn't have a weight. So we're going to write infinity. B to E is 132. And B to F doesn't have a weight, so I'm going to use infinity. C to D is 289. C to E is 160. And C to F is 125. D to E is 84. And D to F, well, D isn't connected to F, so I'm going to use infinity. Last but not least, E to F is 191. So we've now filled out half of our initial time matrix. And as I mentioned before, we've got an undirected graph, so we can actually reflect our time matrix to find the other values. And that's what I'm doing currently. I'm reflecting it and writing in the values for the lower part of the matrix. So now that we've done that, we're asked to perform the first iteration of Floyd's algorithm. So I'm going to shade in column A and row A. So I'm going to do that here. Row A is here. And column A is here. So these values are going to remain unchanged for iteration 1. So I'm going to add these values in right now. And again, the leading diagonal are all going to be dashes. So I can copy these values down. And now I can start to consider whether there's any routes via A that make the route from one vertex to another smaller. 72 is smaller than 95, so that's not going to change. Infinity, we will need to update. So to go from B to D, I'm instead going to go from B to A, and then from A to D. And that's going to give me a total distance of 57 plus 150, which is 207. My next value, 132, is larger than 57 plus 63. So the result of 57 plus 63, 120, is going to replace 132. I've got another infinity. 57 plus 230 is 287. And whilst I've been doing this, I've been forgetting to update my root matrix. You can complete the root matrix afterwards, but it's going to be really awkward identifying which values you've changed. So my recommendation is when you change a value, also update the root matrix for that respective value to the new letter. And in this case, it's going to be the letter representing the iteration we're on. So the first iteration is going to be A, so I can add in A's for B to D, B to E, and B to F because these three values have reduced. So carrying on, 289 is going to become smaller. 150 plus 95 is only 245. So I'm going to add in that A right there. 160 is larger than 95 plus 63. So that's going to be reduced to 158. I'm going to get another A. 125, on the other hand, is definitely smaller than 230. So I know there is not going to be a change there. The same can be said about 84 being smaller than 150 and 191 being smaller than 230. The last value we've got to update is this infinity, going from D to F. And we can update that with a distance of 380. And that's going to update the value going from E to F. That's going to become an A. Sorry, not E to F, D to F. That's going to become an A. And because we've updated these values in the root matrix, we can actually reflect this change as well. The change is going to be reflected down here, and then here, here, and here. And now we can reflect the rest of the time matrix. We're going to get 72, 207, 120, 287, 245, 158, 125, 84, and 380, and 191. And then when we're filling out a root matrix, any value that we've not yet changed, we're just going to copy from the root matrix previously. So doing that, we're going to get A, B, 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 C, 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 D, 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 E, 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 and E, and finally F, 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 and F. So how many marks is this worth? Well, setting up the initial time matrix is worth 1 independent accuracy mark. The general concept or the general application of Floyd's algorithm is worth a method mark. Importantly, you've got to reduce at least 2 values correctly. So as long as 2 of these 12 values have successfully changed, we're good to go. And finally, the accuracy mark is achieved if you correctly perform the entire first iteration. We're now told that the final time matrix is shown here. We're told that we need a route that minimises the total time taken to traverse each road at least once. But we can start at B and finish at E. This sounds really familiar and sounds like a route inspection problem, and it is. So we've got 6 vertices, all of which have an odd degree, and we can tell that by looking at them. So A has degree 5, B has degree 3, C has degree 5, D has degree 3, E has degree 5, and F has degree 3. So all 6 vertices have an odd degree. So we need some sort of way to make it a simpler problem, because otherwise we have a lot of combinations to consider. So we need a route starting at B and finishing at E. That means that B odd and E odd are absolutely fine. We don't need to worry about B and E. So we only have to worry about A, C, D, and F. And all the combinations of connecting 2 pairs together. So we could connect the pairs AC and DF. But if we connect AC and DF using the shortest route between the pairs, AC has a distance of 95 and DF has a distance of 275. which is going to give us a solution of 370. So if we try making ACDF even by connecting A and C together with the shortest path and D and F together with the shortest path, we're adding a weight of 370. Let's try AD and CF. I can see from my matrix that AD is 147, and I can see that CF is 125. That's going to give me a value of 272. Last but not least, I could do AE, sorry, not E, AF, and CD. And AF has a distance of 220, and CD has a distance of 242. Those add up to 462, which is really large, I'm afraid. So the best solution here is this 272. So it's really tempting to say that you need to traverse AD and CF twice. However, this isn't the case. We need to traverse the paths that go from A to D and C to F twice. So we actually need to consider where these paths are. So let's see, how can we get from A to D in a distance of 147? And I can look at my diagram. A to D is currently 150, but if I go from A to E and then E to D, that's going to give me the 147 that I'm looking for. So instead of this statement here, I need to traverse AD, sorry, not AD, I need to traverse AE and ED twice, and then I need to consider CF. CF needs to be 125, and actually CF is 125, so that can just be traversed twice. That is an edge. So I need to traverse these three edges twice. So, mark-wise, what are we going to get marks for? So we're going to get marks for considering pairings of these four odd nodes. So mark for considering pairings of these odd nodes. But if you include B and E, you won't get that method mark. You then get 2 accuracy marks for the process of adding these numbers. So you're going to get 1 accuracy mark for doing 1 correctly, and then another accuracy mark for doing all 3 correctly. And finally, an accuracy mark for writing the edges you need to traverse twice. Finally, we've got part D. And part D asks us to write down the length of a route. If we're traversing AE, ED, and CF twice, we're adding a weight of 272 to the existing graph. So we just need to know what the weight of the network is. Unfortunately, we're told this, it's 1,648. So when we do this question, we just need to say that the length is that 1,648 for the entire network, plus the 272 that we're doing twice. And if we add these together, it's going to be 1,920. And we should really add the units. And the units is the time needed to travel along each road in minutes. So we're going to get 1,920 minutes. If you don't include the units, it's not the end of the world. But on other exams, it might be. So mechanics requires units a lot, but decision fortunately will let you off with that. So until next time, thanks for watching.